The serial peripheral interface bus is a synchronous serial communication interface and commonly used by microcontrollers for communicating with one or more peripheral devices. There is always one master microcontroller which controls the peripheral devices. There are three lines common to all devices: MOSI, master out, slave in. It's a master line for sending data to slave devices. MISO, master in, slave out, slave line for sending data to master. SCK, serial clock, clock pulses for data synchronization between master and slaves. One line specific for every device. SS, slave select, or CS, chip select. Master tells the slave that it should wake up and receive or send data. As you see it here, our master is Arduino Megap with RAMPS shield and three other slaves represent the TMC2130. We can have n number of slaves. Most important thing is each slave to have specific cable select pin. We will talk about this later on Marlin configuration. I have soldered 4-pin headers on top of the driver for SPI connection, but it is not just enough. We need to desolder standalone bridge and create two new bridges on CFG4 and CFG5 like this. It is a little bit tricky to make bridges on such small pads, so I decided to show you how I made mine. After I desoldered the standalone bridge, I cleaned the solder tip and melted some fresh solder. The trick is I will touch the pads that I want to bridge with this melted solder and move the soldering iron tip up. As you see, bridges are ready. This is how the board looks like after I cleaned it. This is my wiring diagram. Each driver is using its own chip select pin. I used DuPont connectors to prepare my cables. This is how it should look like after you finish cabling. I have opened Marlin source code with Arduino editor. We need to go to configuration ADV for TMC2130 settings. I'm going to open find and search for TMC2130. As you see, we reached to the TMC2130 section. Now we will tell that we have TMC2130, and so that we need to remove the double slashes for it. And let's go down. Okay, in this part we will tell that which axis has the TMC2130 driver. In my current setup, I am using it for X and Y axis. So I will remove the slashes. Okay, this is the stepper driver settings. At here, the setups are already in the default values. For the current setup, default is set to the 800 RMS. If you would like to reach to the peak current, you can multiply it by 1.41, so that will give you the amount of the maximum current. I would like to change the stepper motor currents to 600 RMS. It is what I need for my current setup. At here we have also interpolate. It's how the TMC2130 activates the 256 microsteps inside itself. So as the default value, it's true and I'm not going to change it. If you feel that your holding current is too much, you can reduce it with this value. Currently it is 0.5, so that it will be, in my current setup, 300 milliamps. So if you need more current, you can change it at here. Okay, at this part, it's already defined that we are going to use the stealth chop mode. I'm not going to change anything at here. For the motor driver status, I'm not going to use it. but I'm going to enable the debug mode because I want to use the M122 command to see the registers of the driver. I will enable it because I want to see that if I connected the drivers correctly or not in the SPI mode. If I connected correctly, it will show me the valid register values. If not, it will just show me the FF values. I will show it to you later. And for the driver status, we can see that it has the over temperature pre-warning flag, and you can clear this flag, report these values, etc. I'm not going to use any of them, so I'm just skipping this part too. I'm not going to use the hybrid mode because I'm quite happy with the stealth chop mode. But if you would like to customize your setup, you can read the descriptions and change them in the way you want. For the sensorless homing, I will compile the sketch later and I will show you a video that shows how it's working. So this is the place that I'm going to remove the dashes, TMC debug. It will allow me to run the M122 command. Also, I forget to tell you that I'm going to change the chip select pin. Let me see where it is. Okay, as the default, chip select pin is 53 and 49 for X and Y axis. It's located in the aux3, and I'm currently using an LCD driver that's using this part already, and the D53 and 49 is already occupied by this driver. So I'm going to move them to the aux2, and I will use the D63 and D59. So I'm going to show you how to change it. For that, we need to go to the pins, and my board name is RAMPS, pins RAMPS file. Okay, here it is, and seek for XCS. Okay, as you see here, we have the chip select pin for the X and Y axis. The default values are mentioned at here, and I'm going to change them according to my setup. So I will make them 63 and 59. So let's start changing it. 63 for the x-axis, and for the y-axis 9. Okay, so I already completed my setup. Let's compile and upload it. So uploading is done. I'm going to open the serial monitor. I enabled the debug command so that I can use M122. As you see it here, I can get the details for the X and Y axis, and I can also read the driver registers. If the driver registers start with the 08, it means that it's connected correctly. If you see OFF, FF, and if it continue all the characters as F, it means that you have cabling problem or the SPI connection is bad. You must check the cabling. And I would like to share some other comments that might be useful to you. As you see, current set current is 600 milliamps. We can change it on fly. M906, for example, x-axis, and set it to 700. Okay, now the x-axis became 700. If you would like this value to stay in the EEPROM, you can register it to the EEPROM with M500 command. Currently it will not work on my setup because I not enabled the EEPROM yet, but as you see, it will give EEPROM disabled error. The configuration part is finished. Next step is how to enable the sensorless end stop. After we made sure that the SPI connection is working properly, now it's time for us to disable the TMC debug because we do not need it anymore. And for this I am adding slashes in front of it. And as the next step, I would like to show you the sensorless homing. So to able to use the sensorless homing, we need to remove the dashes in front of the definition. And as mentioned that here, we need to change also X and Y axis home bump value to 0. So let's go up and try to seek for it. Since it's better to write in search. Okay. And I'm going to make both of them 0. And now it's time for us to disable the end stop. So I'm going to disable the end stop because when the stall guard is active, TMC2130 sends plus voltage. So I disabled all end stops to be able to show it. And for this setup, it's fine to run. So let's compile it. I was lazy to solder the DAC 1 pin to the TMC2130 driver, so that I am using a jumper cable just to demonstrate to you, because I'm not going to use sensorless homing on my setup. So DAC 1 port is the port which is closer to the potentiometer, and I already make my jumper cable touch to there. Okay, the uploading is done. Now I'm going to open the serial monitor and I will send G28 to show the homing process. Okay, when I am not holding the stepper motor, as you see, it's turning. So now it's time for me to hold the gear. As you see, when I hold the gear, it's stopping, so that the end stop is working properly. If you want, you can change the values and make it much more sensitive. And for that, you can find the details at here. You can send the M914 and the name of the axis you want to use, and the value, the smaller values is making it more sensitive, and if you increase it, it will be less sensitive. So you can calibrate it like this. Thanks for watching. I hope this video will be helpful for you to understand how to use the SPI connection with TMC2130 and RAMPS port. If you have any comments, please write it to the comment section. And if you like this video, please give it a thumbs up. Thanks for watching.